Hello everyone, my name is Eric Jacobson here, and I'm here to present to you a quick description of a substance that has been taking place in modern physics for the last 100 years, and this is the Bose Einstein Condensate. So, for today, we'll be talking first about the different states of matter, and then we'll move on to the history of the theory and the creation of this state of matter right here. After that, we'll go to talk about the differences between bosons and fermions, followed by the different kinds of bosons. Lastly, we'll talk about the creation of this Bose-Einstein condensate and the applications that come from it. All right. As you probably remember from high school or elementary school, there are three standard states of matter that we encounter in everyday life. But if you've looked a bit further, you also know that there are other ones such as plasma, which would be a state of matter that you would find in stars, and the Bose-Einstein condensate is just another state. Uh, so, looking into the history of this, it started in 1924 when Satyendra Nath Bose used and created some quantum statistics to find some interesting facts. He sent this over to Albert Einstein, who not only translated and published this work, but also built up on it to theorize the Bose-Einstein condensate. And this is where it started. But at the time, the instrumentation that was available and the machinery could not bring any substance down to temperatures cold enough to actually have this substance in existence. But people tried for a very long time, and in 1995, two separate groups, one at the University of Colorado and another one at MIT, were able to recreate the temperatures required for this substance to exist, and they ended up winning the 2001 Nobel Prize in Physics for that. So before we go on to talk about what a Bose-Einstein condensate is, first we're going to do a couple of things. So looking at the two elementary kinds of particles here, we have bosons and fermions. Bosons are called the force carriers, whereas fermions are they give properties to matter. And another interesting thing is that bosons have no restriction on how many of them can be occupying the same quantum state, meaning that they could have the same spin and other properties as well, whereas fermions can't. They're limited by the Pauli exclusion principle. Also, bosons have to have integer spins, such as 0 or 1, whereas fermions don't. And a good example of this is electrons. And you'll see sometimes electrons that are orbiting in the same shell have to have opposite spins. So one of them could have a plus 1/2 spin and the other would have a minus 1/2 spin. So that should give you a little bit of an idea right there, but we won't go into further depth for this over here. Next, bosons are split into two categories, the elementary bosons and then the composite bosons that are built up on this. So on the left side over here you can see the different kinds of bosons, photons. These carry the electromagnetic force. W and Z bosons carry the weak force. Gluons, these are the fundamental carriers of the strong force. This is the force that holds the nucleus of atoms together. It prevents the repulsive forces of the protons from actually being pulled apart together. And then there's the Higgs boson that was recently found at the Hadron Collider. And lastly, there's the theoretical graviton, which would be the carrier of the gravitational force. But this has not been found yet, and physics is still trying to find this out over here. And composite bosons can actually be fermions, or they can be bosons themselves. Think about something that would have half-integer spins that add up to 0, such as electrons, two electrons in the same shell, one with the plus 1/2 and the other with the minus 1/2. When you add them together, that would equal 0. Obviously, there are other properties that would also have to be related to that of a boson, but that should give you a bit of an idea right there. So now that we know a little bit about bosons and what they're not and the different kinds of bosons, we can actually start to talk a little bit about what we're trying to do in this presentation, and that is the Bose-Einstein condensate. Essentially, it's just a state of matter, but not just any. It's the state of matter with the lowest quantum energy state. And what happens when you get different atoms to be at this lowest quantum energy state, since they are bosons, more than one of them can have the same quantum state. And because of this, you can have a group of atoms behaving as a single atom right here. But to do this, there are certain things that are required. First of all, this starts off as a very dilute gas. It's actually 1/100,000th of the density of atmospheric air. You're reading that correctly there. That's an incredibly low density right there. Also, it has to be at an extremely low temperature, which is in the nanokelvin temperature range. And this is what actually prevented it in the past from scientists being able to recreate this substance, because as it's being said, it's actually the coldest substance on Earth right there. So you can imagine how difficult it's been for years for scientists to actually be able to get a substance to be as cold as this right here. So now we'll be looking at creating a Bose Einstein condensate. We'll start with a diffuse gas in the sense that its motion and its gradients, such as pressure and temperature, will be completely random. And you will contain it through an electromagnetic field and different laser beams that will hold it in different axes, as you can see in the figure on the right. You will also use other lasers to cool it, and this might sound a little weird that you'd be using lasers to do this since they're supposedly very hot, but the way they do it is that these lasers send pulses instead of a continuous beam to the atoms that are vibrating inside. And remember, light has momentum, so it can impart force onto these atoms. And by having these lasers pulse at a frequency that is out of phase with the atoms, you'll actually be removing kinetic energy from these atoms. Slowly, but you will do it right there. And if you remove kinetic energy from a substance, you're actually lowering the average temperature of the substance that you've removed this from. The only thing is that by doing this, you can only get it down to the microkelvin range, which isn't enough to actually create this substance. So another step has to take place. And this is done with what's called evaporative cooling. It's a technique that's been used in other things as well, but over here, the way that it'll work is that the electromagnetic field will be slowly removed in the z direction or in height. So this field will be dropped this way, allowing the particles with the highest kinetic energy, which would be at the top, or the hottest atoms, to actually escape. And by doing this, by allowing the particles with the highest kinetic energy to escape, the average kinetic energy of the rest of the particles will actually drop, and you can actually bring it down to the nanokelvin range. And once you have it there, a lot of the atoms, if not all, will go into the same quantum state, so long as they're bosons right here. And that is how you create this over here. And now in the next slide, we'll get a better idea of the concentration of atoms that are being put into the same state and what that looks like. So building up on what I was talking about earlier, if you look at the probability density function on the left, you can see that at the beginning, many of the particles are going to be in the same state over here, but a lot won't be there yet. As the temperature continues to drop, this density increases up to a point where pretty much all the particles are in the same state. Similarly, on the right, you can see that the different quantum states over here that could be occupied. But as the temperature drops, eventually all the particles end up in this state over here. And that is exactly what we're trying to do to create this Bose Einstein condensate. So, with this being able to create this Bose Einstein condensate, a lot of applications are starting to come about from this that makes it pretty exciting for the future. One of the biggest ones is atom lasers or atom optics field, and this will allow many things such as painting integrated circuits at a nanoscale right here and precision measurements. And this is possible because, similar to a laser, a steady stream of atoms with all being in the same quantum state and frequency will be able to be fired out of these atom lasers right here. And this will completely change the way certain things are done. Remember that the frequency and wavelength of atoms is extremely small, so this could have some positive effects in physics and the whole science and engineering field. The next thing is quantum computing. And even though quantum computing already has a lot of interesting things going on, most of it's on the digital side. Very little has been done on the analog side, and this will be similar to what was done in the past with analog classical computers, where they used operational amplifiers to do a lot of things, and it'll be similar to that as well. So actually using physical results and changes to be able to get information from there. And the last thing that I want to talk about is how you can use Bose Einstein condensates to study analogous physics in completely different things, such as neutron stars. And you might be thinking, these are completely different temperatures and conditions and everything. How can this be the same? But it's the substances themselves behave in similar ways, so you'll be able to use Bose Einstein condensates to get an idea of what things could certain substances and states in other places could react to different things, and start getting valuable information from there. And that's everything for this presentation. I hope you learned a lot right there and enjoyed the presentation. Thank you very much.